Okay, guys, so here we are. This is section 4.9. Last section, chapter 4, kind of really belongs in chapter 5, though. I'm not sure why exactly it got put in chapter 4. Title section 4.9 is anti-derivatives. This is the thing I've been warning you about all semester, that at the end of the semester, we're going to do things backwards. Okay? So in the first part of the semester, we would know, if we were talking about like a physical application, as a physicist would know that where a position is of a particle and want to find velocity, and that would be to take a derivative. But now we're going to say, well, what if you know the velocity of it and you want to turn velocity into position? Well, if going from position to velocity was a derivative, then going the other direction should be an antiderivative. Okay? Or if we're talking more of an engineering example, if we talk about a rate at which something is changing, can we figure out how much water leaked out of it? So can we turn a rate of change into a total change? Right? Well, there's a bunch of other applications. There's applications in biology and all this stuff. But in all these cases, what we're looking at here is we're looking at applications where we need to find an antiderivative. So let's start laying down some language. We are going to be using a series of lowercase and uppercase. So I'm right here. In each case, the problem is to find a function f. Notice it's a capital F, whose derivative is a known function f. Notice it's a little f. So we have little f's and big f's. And what we are going to argue here is that little f is the derivative of big F, or if you want to look at the other direction, which we are going to from this chapter forward, or this section forward, big F is the antiderivative of little f. Okay. I also want to point something else out, and it's an English thing. You'll notice here we are using the article an antiderivative, not saying the antiderivative, because unfortunately there are functions out there where multiple original functions could arrive at the same derivative, or conversely, there are functions out there, little f's, that have potentially multiple big F's that would exist for their antiderivatives. Okay? So for example, we're going to write a function f whose derivative would be 3x squared. Well, a function whose derivative could be 3x squared is x cubed. And that would mean that x cubed, the function f of x, capital F of x, sorry about that, equals x cubed, is an antiderivative. Right? So we're making antiderivatives. We're just doing everything we've done so far backwards. Right? But that's not the only one. What about this? Could x cubed plus 1 be an antiderivative of 3x squared? Or how about x cubed plus 5? Right? And so what we say is, when we find the antiderivatives, we're going to look for the general form of the antiderivative. In this case, the general form is going to be x cubed plus some unknown constant c. And what this c right here represents is it represents any constant, because when you took the derivative of that any constant, it would disappear and it would no longer exist here in that derivative. Right? So remember, going from here to here is taking a derivative. Going from here to here is taking an antiderivative. Constants would disappear when you took the derivative, and that's why we have that possibility of an unknown constant having been there. Right? If the thought of that intrigues you, differential equations. You'll spend an entire semester working with finding antiderivatives and figuring out what those original constants could have been. Okay? But most importantly, what this leads us to is it leads us to our first theorem. And our first theorem states that if capital F is an antiderivative of little f on some interval I, now be careful here, this could be all real numbers. It could be negative infinity to infinity, or it could be something small, a to b. Okay? It doesn't really matter. Okay? It's just some interval. Then the most general form of that antiderivative is going to be that function f of x plus an unknown constant c. Right? You'll see it said read as an arbitrary constant also. Unknown, arbitrary, same difference. Right? The process of finding an antiderivative is called antidifferentiation. Right? All right, so let's take a look at some examples. And we're going to go through these rather quickly because you know all these already. So first off, we're going to say, what is the most general antiderivative? And so whenever I see that language right there, I know that my answer is going to be big F of x is going to be equal to something plus c. right? And then I need to find the most general antiderivative of, in part A here, sine. So which function, when you take its derivative, gives you sine? That's right, negative cosine. Right? So the negative of cosine, because if you took the derivative of cosine, would give you negative sine, so you got to stick an extra negative in there to get you back to positive. Negative cosine x plus c is the most general antiderivative. How about part B over here? What function, when you take its derivative, do you get 1 over x? Well, that would be the natural log of x, and that would be a pretty good answer, but putting a plus c on it makes it the most general antiderivative, makes it the correct answer. All right, in part C here, we're looking for a formula, essentially. What we're saying is, what would happen if you took the antiderivative of x raised to a power where that power was not negative 1? Because if that power was negative 1, we'd be over here, right? So we don't want negative 1 if it's just any other number. Well, the rule for taking derivatives is to reduce the power by 1. So the rule for taking antiderivatives would be to raise the power. The rule for taking derivatives says multiply by that exponent. So then the rule for taking antiderivatives would be to divide by that exponent. And then that red right there would be the antiderivative, but we don't want the antiderivative, we want the most general. So we're going to stick a big old plus c on the end, and that's going to give us our most general antiderivative. If you're ever concerned that you're incorrect, all you have to do is take a derivative of your function, capital F, and see if you get back to your lowercase f. For example, what's the natural log? 1 over x, and I'm good. The constant is always just going to disappear. If cosine is negative sine, put another negative into it, it would take us to our positive sign, so we're good there, right? So my job is to be able to find antiderivatives. Now, I had a whole table of how to take derivatives, so now I've got a whole table of how to take antiderivatives, right? I'm going to work my way down this left-hand column over here, and then we'll move to the right-hand column. Okay? So the first one says, if you are asked to find the antiderivative of a constant value k, just some number, 5, 7, 12, negative 14, whatever it is, the particular antiderivative, now that's an interesting language, particular antiderivative just means ignore the plus c. If we want the plus c, then we're going to say the general antiderivative. So the particular antiderivative of k is going to be k times x, right? The particular antiderivative of k times some function f of x is going to be k times the antiderivative of that function, capital F of x. Working down the left-hand side, the antiderivative of f of x plus or minus g of x is going to be the antiderivative of f of x, capital F, plus or minus the antiderivative of g of x, capital G of x. The next one's one we already looked at, x to the nth is going to become x to the n plus 1 divided by n plus 1, but this is only true when n is not equal to negative 1 because that gives us our logarithm rule. Right. The next one should be your favorite. What's the derivative of e to the x? E to the x. So what would be the antiderivative of e to the x? E to the x. We got a couple of arc-trig there that we should know. 1 over 1 plus x squared takes us back to arctangent. Right? Now you should know these in this direction, right? You should know all of these in this direction. All we're doing is just saying, if you know them in one direction, that is how to take a derivative, you should also know them in the other direction, that is how to take an antiderivative, right? Now there is one, and I'm going to circle it right now with the pink here, that sometimes causes people trouble. They want to say, why does absolute value show up? Because they remember this from taking derivatives. They remember that taking the derivative, the natural log of x was equal to 1 over x. So then the argument is that, well, when you take the antiderivative, then the antiderivative of 1 over x would just take you right back to natural log of x. How come there's an absolute value that shows up? And what this deals with is it deals with what the original function is in the process of antidifferentiation versus what the original function is in the process of differentiation. Because the original function is what defines the domain for your expression. So when I circle this right here and I say that this is the original function that we're starting with to find an antiderivative, there is nothing about 1 over x that says that x cannot be a negative number. So the domain of this expression right here, 1 over x, would be negative infinity to 0 union with 0 to infinity. I mean, it obviously can't be 0 because we're not allowed to divide by 0, but there's nothing about that that says x can't be negative. But when you anti-differentiate and you introduce logarithms, logarithms don't like negative numbers. So that argument of that logarithm right there can't be negative. And so how do we force something that can't be negative to be positive? We wrap it up with absolute values. Now, the reason that this issue does not exist over here when we're taking derivatives is because we started with the logarithm function, and that implied that the domain was 0 to infinity, where negative numbers were not allowed to be used. So since we started with logarithm when we were told to take a derivative, we didn't have this issue, right? That's why that shows up. Some people are really particular about it. Other people let it slide and aren't so upset if you leave out that absolute value. Okay, just be careful though. The homework is particular. All right, we already looked at this one. This next one here, we have the antiderivative of sine is negative cosine. The antiderivative of cosine is sine. The antiderivative of secant squared is tangent. Cosecant negative cotangent. Secant tangent secant. Cosecant cotangent negative cosecant. These are all just the trig rules written backwards. We memorized all the trig rules, so guess what we're going to do? We're going to memorize them all backwards. Okay? And if you want to turn any of these particulars into a general, all you have to do is add a plus c on the end. All right, let's take a look at a couple examples here. Our job is to find the most general antiderivative of each of the following. That means it's all going to have a plus c on it. If here's my function little f, what would big F of x look like? Okay. Well, when I'm looking at this, I'm seeing 3 times x raised to the first power. And the rules tell me that the 3 just drags along. Because I'm taking an antiderivative, instead of subtracting from the exponent, I'm going to add to the exponent, and then I'm going to divide by that new exponent. And if I want, I can then clean that up and call that 3/2 x squared plus c. Okay? Moving on to letter B. I'm looking at this, and I'm not seeing 1 over x squared. I'm seeing x to the negative 2. We almost always rewrite, don't we, when we're taking derivatives? So what are we going to do when we take antiderivatives? Rewrite. The only time we don't rewrite is this one right here. So then I'm going to find the most general antiderivative. I know it's going to be something, plus c. If derivative rules say subtract from the exponent, antiderivative rules will say add to the exponent. So what's negative 2 plus 1? That's going to be a negative 1, and we divide by that new exponent. And so I'll clean that up a little bit and call that f of x is equal to negative 1 over x plus c. Okay? Moving on to problem letter C. Problem letter C. Sounds weird. Anyway, hey, this one has 3 terms. But that's okay. I'll just anti-differentiate each term individually and put a plus c on the end. The first term, 3x to the 4th, the 3 drags along. X to the 4th becomes x to the 5th over 5. The second term, the negative 5, drags along. The x squared becomes x cubed over 3. And I didn't leave myself enough room. The last term, x becomes x squared over 2, and of course plus c. I'll clean that up and write that prettier. I've got 3/5 x to the 5th minus 5/3 x to the 3rd plus 1/2 x squared plus c. Now, if you're looking at this saying, I don't like fractions, well, you are out of luck because antiderivatives love fractions. Oh my gosh, they're the favoriteest thing ever. All right, letter D over here. What are we asked to do? Again, we're finding the most general antiderivative. I don't see roots. I see this as x to the 1/2. So what will big G of x be? Okay. So the rule still holds. Little function turns into big function, if you will. Lowercase g turns into capital G. All right. So the rule says add 1 to the exponent. So 1/2 plus 1 is going to give me 3/2. And then I should divide by 3/2, but that's just weird to write it like that. So I'm just going to do the math in my head and say dividing by 3/2 is multiplying by 2/3. And of course, I'm going to put a plus c on the end because we are always adding the plus c to get it to be the most general, not just a particular, but the most general antiderivative. Oh my gosh, there's more. This is so exciting. I love this stuff. Here is our function f of x. My job still is the same. Find the most general antiderivative. So little f is going to turn into big F. The 2 just drags along. Antiderivative sign. Let's see. Antiderivative sign. I believe that's negative cosine of x. And of course, plus c. Now you notice I wrapped that up in parentheses. And why did I do that? Experience has shown me that if I don't put those parentheses on there, that sometimes turns into this, which is horribly incorrect, and we don't want that. We want to make sure that that coefficient 2 gets multiplied by negative cosine x, or we get a negative 2 cosine x plus c. Now, I know there's at least one person watching this video right now who's saying, do I really need to write this line if I know it's just going to become this? Can I go straight there? I am hoping that that's what you want to do. I'm hoping that you will get there. Okay? I'm going to continue writing that intermediate step for a little while until we get more comfortable with this, but ultimately, it would be awesome if you could go straight from here to here and not write the red line. Okay? So if you're wondering if you can do that, I would like to see that. All right, g of x is equal to 1. Well, that's just a constant. So what would that mean about its antiderivative? Well, the antiderivative would be the constant times x for a particular antiderivative. But if you want a general antiderivative, we add that plus c on the end, or we could just call that x plus c. Our general antiderivative. Man, I'm just burning through these. These are so much fun. I hope there's more. Oh, there's even an example here. Find all functions g such that g prime is equal to 4 sine x plus 2x minus root x divided by x. This is outstanding. So they've given me a derivative, and they've asked me to find a function g that would give you that when you took its derivative. So if I'm going from g prime back to g, then I need to take an antiderivative. That doesn't look fun to do, but that denominator is a monomial. And if that denominator is a monomial, I can rewrite that. So I'm first, before I even try to take an antiderivative, I'm going to rewrite g prime of x and say g prime of x is equal to 4 sine of x plus 2x to the 4th minus x to the negative 1/2. Now, if you're wondering where that came from, I rewrote this fraction as 2x to the 5th over x minus x to the 1/2 over x, and then I simplified. Now I have an expression that contains 1, 2, 3 terms, and my job is to find the antiderivative of each of those 3 terms. Okay? So first term, the antiderivative of 4 sine x, I've done that one already. It wasn't a 4 before. It was a 2 before, but I know what's going to happen. It's going to give me a negative 4 cosine x. Right? 2x to the 4th, that's going to be the 2 times x to the 5th, add 1 to the exponent, divide by that exponent, so 2x to the 5th divided by 5, and then minus, let's see, add 1 to the exponent is going to give me x to the positive 1/2 divided by 1/2. Now that answer is almost right. It is a function that works, but I'm supposed to find all functions. So I'm going to put on a big old plus c to make it the most general antiderivative. But if you know nothing else about me, this is unacceptable as it is, and I will clean this up and make it pretty, wrap it up, put a bow on it. We have g of x is equal to negative 4 cosine of x plus 2/5 x to the 5th, and then dividing by half means multiplying by 2, so minus 2 root x plus c. How gorgeous is that? I love calculus. This is probably the best day ever. I love antiderivative sections. Hey, look at this. Extra examples. That means I can do more. This video is going to be long. All right, so what's wrong with this one? Lots. I can't do it like that, so I'm going to rewrite it. So I get that f of x is equal to, and why can I rewrite it? I can rewrite this because the denominator is a monomial. All right, so what is x divided by root x? Well, that's going to be, whoa, I don't want you guys anymore. Go away, arrows. Go back to green. That's going to be x to the 1/2 plus x to the negative 1/2. Okay? So I haven't taken an antiderivative yet, so it's still called little f because all I did was just algebraically manipulate it, so I could take an antiderivative. Now I'll take that antiderivative, its name changes now, it's capital F, add 1 to the exponent, x to the 1/2 becomes x to the 3/2, divide by 3/2, plus x to the negative 1/2, add 1 to the exponent, you get positive 1/2 divided by 1/2, and then of course put a plus c on the end because I want all my credit. Now I need to clean it up, make it look pretty. So what will that function, the general antiderivative, be? Dividing by 3/2 is multiplying by 2/3. 2 times x to the 1/2 plus c. Now, do you feel any need to take this and rewrite it as a fraction since the original problem was handed to you as a fraction? Because if you do, please go ahead and do that. The rest of us are going to say no. All right, moving over here to part B. My job still is the same. I need to find the most general antiderivative for this function, but I have no clue what to do with this bad boy. Sine divided by cosine squared, that's just ugly. But you know what I always see whenever I see sine divided by cosine? I always see a tangent in there. So maybe if I do something like that, some trigonometric simplification, and think of this as sine x over cosine x times 1 over cosine x. Maybe that'll ring some bells. Because isn't sine x over cosine x tangent x? And isn't 1 over cosine x secant x? And so then I've got the little g of x is equal to tangent x. That's an ugly secant x. Let's clean that up, make that look prettier. And what is the antiderivative of tangent secant? Or maybe you would remember it better if I said it's secant tangent. Well, the antiderivative of secant tangent is secant. The derivative of secant is secant tangent. So the antiderivative of secant tangent is secant. But that's only a particular antiderivative. If I do this plus c, then I've got the most general antiderivative. I'm going to leave it right there. In the next video, we'll pick up here with initial condition and particular solution problem, which add another level of complexity and joy. All right. See you guys on the next video.